There.
She was on or she is on?
No, it's recording now.
Okay. Hey, Jasmine. Is she live?
No.
No. Oh, figures. But that's probably why, because she can't be in class, so you have to record it. All right. Well, we still got one more minute before we start. Anybody have anything serious? Any trees on any houses or anything? We're just always glad when we see trees laid down right beside the house and not on it. Ashland's neighbor had a tree on their garage, but it didn't crush it. It just kind of laid down on it and cost them $1,000, but they had some kind of lift thing and they lifted it off and his garage is fine. So he did good. Yeah. And then my oldest daughter's buying that house. It was built in 1912. And so we were all panicked it was going to get blown apart, but we're going, hey, it's been here since 1912. It's lived through a couple other hurricanes, so it made it. It made it. We'll see. Our trees, and your tree didn't come down either. I was looking at your tree today. Yikes, yours is right over your roof.
Oh, I know it is. Every time, and
it's going to cost so much money to get them cut down.
At night, the branch,
Was it
there's
squeaking?
one over
Touching the roof.
over the attic, and it kept going. Like, I thought it was one of the kids, and I'm like, what is that sound?
There's some trees we walk by at night, and they're so big, and there's trees where they're all kind of almost like a couple of seedlings grew up together, and there's all those trunks, and they're so big, but they rub and they go. It's really creepy.
It sounded like I thought of the witch in the attic that Papa
And then we got freakish neighbors that go all out with Halloween.
Oh,
They've
they're
got this
awful.
horrifying. They took down their skeleton only because of the storm. They love their skeleton so much. He's like, he's taller than the house, and the houses are tall. He's like probably 30 feet high. He's giant.
The one that they kept out.
Yeah, they love him so much they kept it out. Because I said something to him.
Now they bought a second one and they're carrying a pole with 3 children.
Yeah, it's really sickening. I'm gonna drop them an anonymous note, but they got a ring. They'll know it was me. I'm trying to practice. How can I drop them the anonymous note without them catch me on the ring that I threw the note in the yard? Going, this is over the top. My grandchildren are terrorized. It looks like cannibalism. It's really sick.
My kids in the bedroom.
It's really gross.
We can't walk down the street.
So we're finishing chapter 4. Not graded.
Oh gosh.
She was doing this last night while she was watching a TV show. I saw her in person.
I'm watching silent.
Okay. So we're going to finish up chapter 4. And you know what I did? I did this really cute video of Cadence and Savannah doing their lab, and I didn't send it to y'all. So those of you weren't here, I was going to send you their lab, and I didn't know how to do it. So I do have power, and now I have internet, but I couldn't do it on my phone, and then I didn't do it. So anyways, and I wish I could have told you guys, there's somebody from church who's taking down a big trailer down south. So if something comes through, I'll put it through the email, but he's just taking down water, generators, food, whatever, and just gonna like unload it, just whoever wants it kind of thing. So we could have brought stuff to like donate, but I didn't find this out till last night. So if he's gonna do it again, I'll let you know. It's a great way to just feel like you actually really did something. And anybody follow the coffee and COVID guy? Anybody? Okay. So he did a lot of research on where to donate money, and so he's recommended it's actually a coalition put together by our governor, but the governor said 3% of the funds will go to cover administrative costs up to $30,000, and then 100% of the funds will go to the people. That's pretty good, because Samaritan's Purse claims 5% goes to administration, and the rest goes to the help. But I've read it's more like 8 to 20% goes to administration. American Red Cross never give to them. I'm really serious. 95% of the money pays their salaries. Only 5% goes to relief. So that means if you give $10, only $1 goes, not even $1, goes to the victim. So that's $5. So Samaritan's Purse always does a good job. Not real thrilled about how they handled COVID. That's a whole other story. They're still like all about COVID. I don't even really get it. I just don't understand that. I'm really. You notice that? Because I was a really big fan of theirs, just because I know that they do great disaster relief. I love the shoe boxes. I think that's so fun, so much fun. I love that, and I'm not against it. I'm not saying anything against it. I'm just confused as to how they handled COVID and how they're still dealing. I'm just confused. Anyways, all that to say, if everybody gave $5 or $10, it would be enormous, because obviously there's going to be state money and federal money and stuff like that, but there are people really and truly that won't have a home for a really long time. Ashland's in-laws live in Inglewood, so they left at the last minute because remember, at first we thought it was gonna hit Tampa and everybody was so concerned, and rightfully so, we were like right there, and then it really barreled in. Fort Myers is what took the worst brunt, but Tobias, your grandmother, I heard miraculously survived. Where are you? Where'd you go? There you go. So your mom was saying destruction above and below her, but she no plague came nigh her dwelling. She did great. Which I'm what?
Condo completely gone.
Oh, the condo's gone.
All of the trailer parks on the water side, all.
Wow. That's sad. I know, it's so sad. I'm hoping that a lot of those weren't people's primary residence, but I know some of them were.
Most of them.
So, which doesn't make your loss less, but it's sure good if you have another place you can live. But anyway, I heard them grilling the governor yesterday about their response time. He's going, it was a hurricane. I mean, at one point, I don't care who's in the White House or who's in the governor's office.
The quote of this, the Priuses weren't the people coming,
Yeah.
all that, it
Yeah.
was. all
And
her
we can give a shout out for our
Yes,
linemen.
we can.
They did a great job. They were even better than Irma, and we loved them in Irma. We were begging them. Ashley and I were flying
Every
down
truck
the
I
road.
drive by,
Please,
I'm like, we
it's
love
7 days. We're sweating. Please come hook us back up. We will make you dinners.
Adrian was making fun of me because I kept rolling down the truck window because they were all driving by, and I was like, he's like, why are you doing that? I'm like, because I appreciate them. I brought
Yeah.
power.
Ashlyn was nonstop trying to figure out when we were going to get power. She was obsessed with it. So she met all the neighbors now, and the neighbors found out because they talked to a lineman and said, "We're going to do y'all tonight or in the morning," and they did us in the middle of the night.
So how long did y'all not have?
We three or 4
3.5
days. We got set. It's 3.5 days exactly. Yes, but we had that cool front, so
With
that
my
really helped.
in-laws and dogs.
If we'd been sweating, there'd be claw marks on some of us. Yeah,
It was interesting.
the sweating thing is really hard for us.
We weren't
Which is
sweating, not quite.
we didn't sweat.
That was a
much.
blessing.
Yeah, it was a great blessing. Lots of blessings, but wow, what a crazy mess. So it's that weird feeling, not really survivor's remorse, but in that neighborhood where you're so glad it didn't hit you, but you feel so bad that that's why I always wish they would just go out into the Atlantic and die in the cold water. But anyway, okay, so we're gonna finish up chapter 4, and I know some of you weren't here last week, and we'll just kind of barrel through a little bit of it. The good news is it's not a real hard chapter. Denise is doing very well now. We were supposed to look at this in biology and I forgot. So let's pray. Lord Jesus, thank you for this day that we're here. What a crazy week in between. It's hard to believe it's just been 1 week and it's just odd. But we just ask you to be with the people in the South that are so under duress. And I pray that your church would be your hands and feet for them. And to pray that you would just help us all just to at least remember to pray and just to figure out what can we do to help people that didn't fare as well as we did. And just be with us today as we're trying to regroup and get back on track and help us to learn what you want us to about chemistry today. In Jesus' name, amen. Okay, so we were talking about classifying matter and its changes. So we said that substances can be a pure substance or a mixture, and you missed the cute little video, which I may still send out, of Savannah and Cadence, because what they did was they mixed sand and salt, right? We mixed sand and salt, and now you got a mixture. And then if you wanted to divide it back out again, you'd either have to have tweezers and lose your mind, or we added water and that dissolved the salt and then poured it through a filter which trapped the sand. But now you had salt and water, so then we boiled it. And so then you got the water boiling off and the salt left behind. So it was kind of just real simple. And but that was the whole point. And we were trying to learn the difference between mixtures and pure substances. So let's see, he gave us a nice little chart. Where was it? Oh, it's on page 104, where he just can kind of give you some examples of what a pure substance would be. So table salt is just sodium chloride, so that's a pure substance. He's got a little pile of yellow powder, that would be sulfur. Gold jewelry, even if it was 14 karat gold, wouldn't be a pure substance because they've got other things mixed in it, usually nickel. So if you've got pure gold, it'd have to be like 24 karat gold. That's too soft for jewelry. So that would be a pure substance. He's got an example of a mixture like cereal and milk, Coca-Cola, salt water, Italian dressing. And then he breaks those down into, we could break things down into elements and compounds, and we could break things down into whether or not they're homogeneous or heterogeneous. So elements would be anything on the periodic table of elements right here. So that little yellow pile that was sulfur, I can find that right on my chart. Those are all elements. And it's a compound. If you've got two together, like table salt is sodium chloride, NaCl, so that gives us a compound. Homogeneous means anywhere I take a sample, it's the same. So Coca-Cola is homogeneous. So if you had poured a glass of Coca-Cola and took a pipette and took a sample at the very bottom, one from the middle, anywhere you take a sample, it's going to be the same. It's a mixture, but it's going to be the same. So it's homogeneous. So that's where we get the word homogenize, like homogenized milk. And the little Latin root homo means same. Don't be scared. It means same. Hetero means different. Heterogeneous mixtures then they're not the same everywhere. So if you shook up your bottle of Italian dressing really, really good, it's, for just a brief second, it's sort of all mixed together, but not really. It really quickly, settles out. That heavy stuff, the herbs and spices come to the bottom, and then you've got your vinegar and then your oil on top. So it's little layers. So if you can remember back to physical science, we live in the homosphere. So the air is pretty much the same percentage of nitrogen, oxygen, and other gases, no matter where you go. In the homosphere, it's all the same. The air gets thinner and thinner as you go higher and higher, but it's still all the same percentage. Well, once you leave the homosphere, you're in the heterosphere, different layers. So there's kind of an oxygen layer and a helium layer, and just different. So same thing when we're talking about mixtures. They can be heterogeneous mixtures with varied composition throughout. He talked to you guys a little bit about air there. Okay, how can we classify changes in matter? Because this is another way we can classify matter. We can have a chemical change or we can have a physical change. This is a little bit of a review. I believe this concept is presented in general science, for sure presented in physical science, if you've ever done that class or anything like it. So can anybody give me an example of a chemical change? What about if you mix baking soda and vinegar? That's a chemical change. You end up with CO2 and sodium acetate or something. What about if you throw a log on the fire and it burns up? Is that physical or chemical? It's chemical. It's changed forever. So it's undergone combustion, and some of the matters left behind in the fireplace is ash. Some of it went up the chimney as smoke and different other chemicals and water. But what if you took that log and instead of burning it, you just chopped it into a bunch of little pieces? Is that a chemical change or a physical change? That's a physical change. It's still little tiny pieces of wood. Every little piece of wood is still wood, as we know it, pine tree or oak tree or whatever kind it was. So in the little kid's science book, he'll say, if you can kind of imagine a physical change is sort of reversible, like if you took tweezers and super glue and you glued back together the log that you chopped apart, you could never do that with ashes. You could never form a log from that. So now, it's not a really good definition for chemistry students because we actually are going to learn that there's something called an oscillating reaction where reactions can go back and forth, and so that's not really a good analogy. But physical changes are a change in which the atoms and molecules really stay the same, the atoms and molecules. But the chemical change is where they're actually affected. So if I took a ceramic vase and dropped it, all the little pieces of vase are still the same ceramic material. But if I took that same ceramic vase and I dipped it in some kind of super strong acid, and just kind of like dissolved it, then that's a chemical change. Completely different atoms and molecules are now in that solution than were in it before. Okay, so so we did the lab with the salt and the sand, but I did not put a graduated cylinder into the freezer, but I'll just show you because it's so non-exciting. Where'd my marker go? I'll show you what we did. So if I had one of your graduated cylinders and I put some water in there, let's say I put it right here, I filled it with water, and then I set it in the freezer. When I take it out, it's going to be higher. So usually what I do is I put a little mark, showing where the water level was, and then of course it expands, because you already know that water expands, right? Have you ever put a water bottle in the freezer and it kind of puffed out, or maybe you didn't want, maybe you froze something like a can and it's not good. Sometimes they pop. Now some people get away with freezing soda cans and they don't explode, but some will actually, if there's so much water in that soda, it'll actually explode the can in your freezer. So we know that water expands, and he gives kind of a brief reminder that the reason water expands when it freezes. Does anybody know that reason? Why does water expand when it freezes? Nothing else does that you freeze. Everything else, the molecules get closer together. They shrink. Anybody know? Savannah?
Because of hydrogen bonding.
That's right. If you never know the answer, always say hydrogen bonding. It's probably something to do with it. So we have, water participates in hydrogen bonding, so those little hydrogen bonds, they are attracted to other water molecules. Water is very polar. It's got kind of a positive side and a negative side. So when it gets close to another water molecule, they're attracted to each other. It's very magnetic. Even though it's not unbreakable, you can still jump in a pool. You can still karate chop through the water. But that willingness to participate in hydrogen bonds and the fact that they have that kind of magnetic attraction to one another creates surface tension. So there's a little skin on top of the water. So water striders can just zip right across the top of it. Leaves float, paper boats float. Beavers slap their tail and tell everybody that man is coming, and pool noodles can slap on top of the water, and a belly flop hurts, all those things. So the good thing is, if we didn't have hydrogen bonding, we wouldn't really have life as we know it, especially in the north. So why is that? What would happen in the north if we did not have hydrogen bonding in the wintertime? What would happen when it got really cold? And there's lakes and ponds.
All the water would freeze. All the
Yeah, all the water would freeze, and because it would freeze where? From the bottom up, right? So hydrogen bonding then causes the water to freeze from the top down, because ice floats. Because in water, the three phases, a gas, a liquid, and a solid, their molecules are the closest together when they're in a liquid state. That's not true of anything else. Everything else, they're in the closest state when they're in solids. It's usually like gases, liquids, solids. And that just makes sense, because it's all about energy. You know what I'm saying? They're like, gases they're all spread out. They're all far away from each other. You know, they're here and there. This is why they can take up so much space, and they actually just kind of keep going if nothing contains them. And then a liquid, they're closer together in a liquid state. So, they can move around, but they're just only so far. And then solid, they're really trapped. They're just really tight together. But water they're actually the closest together when they're in the liquid state. So that means that water freezes from the top down. Ice floats. So all the fish are so happy because they have a little blanket on top of them. We're rereading through Little House on the Prairie. We're in the long winter. Y'all ever read the long winter? Boy, was it long. If you missed those books, it's not too late. I can't wait till tonight, finishing it up. So it was so cold that there was blizzards one after the other. I think they were in the Dakotas, and that finally their house was buried in snow, and they were so glad because the house was warmer, because it was like insulated. And Paul just dug a tunnel to the barn to feed the animals through the snow, because it was like buried up. Like Laura would look out her second-story window, and she's looking at the street, which is of course piled with snow because they're in town. Unbelievable. And one time he saved his own life because he got stuck in a blizzard, and he just dug a hole, and almost think of the Inuit people, Eskimo, and the whole igloo thing. So he literally just kind of shelled him out a spot to sleep until the storm passed, and his own body heat kept him alive. So that without hydrogen bonding, winters would be completely different. Animals couldn't survive because they would be frozen. And so instead, they're nice and toasty under that blanket of insulation, under their frozen pond. And then I guess you have to live there a long time to know whether or not you can skate on it. I'm not sure how they determine that, because you obviously want the ice thick enough that you aren't going to fall through it. If you've ever seen It's a Wonderful Life, it's not a good thing to fall through the ice. Have you ever seen the movie? So anyway, okay, so we have phases, and so we go, usually if we add energy to a solid, we can turn it into a liquid. If we add energy to a liquid, we can turn it into a gas. And then reverse, we can take away energy from gases, we can condense them down into liquids, and then we can take energy away from liquids and we can turn it into solids. And we do this all the time. So we call that a phase change, and the words solid, liquid, gas are called phases. And sometimes we're going to put those on our chemical equations. Like if we know something's a solid, we'll put a little S. If we knew something's a liquid, we'll put a lowercase l and a little g for gases. You'll ever solve chemical equations without those phases. They're always the most accurate with a phase listed. So, and sometimes it has a lot to do with how you solve the problem, because later we're going to learn something called Boyle's gas laws. You need to know what are the gases. If you didn't know there was any, if no gases are participating, you can't use Boyle's gas laws. So phases are important to know. Okay, so, and I was going to bring some dry ice. It was going to be so much fun, but Publix has no dry ice, so I'm guessing some people are still using it. Anybody use dry ice to keep their food cold? I always buy it for science, but mine gases off so quickly. I was wondering, how does that work when you camp? I'm just curious. Because I can't even keep it overnight. It's just, I open the cooler and it's just already off gassed. You know, it's just, the bag's empty. It's just gone. Probably a big puff of carbon dioxide came out, but it's colorless, odorless, and it's not toxic, so it's nothing to worry about. But they've got a special cooler in Publix, and they keep dry ice in there, and so it's so much fun to play with. And I would have brought us some, but there was none to be had. And that would be sublimation. So it's a rare thing where instead of dry ice, which is frozen carbon dioxide, just melting and becoming liquid carbon dioxide, it just turns into a gas. So it's called sublimation. It skips the liquid phase. And we see that sometimes in chemistry. And really that should be water, but it's not. Water should really sublimate. It should either be on this planet as a liquid or a gas. It shouldn't be, as a gas or a solid, but instead we have enormous amounts of the liquid water. The planet's almost 70% water, which is incredible. So that's highly unusual, and why they're always looking for water. Anytime they look at another planet or outer space, they always want to find water. Why do they always want to find water? What does that mean if you find water?
It could be life.
There could be life, there could have been life, there could be life in the future. Yeah, it's all about water, and they talk about it incessantly. And of course, anytime there's ice, they're so excited even just about ice, because that's H2O. But ice is, that's not the issue. To survive, you have to have liquid water. So the Ingalls are melting snow and drinking water, you know what I'm saying? And there's a whole interesting science behind, you can't just eat snow all the time. Have you ever read Ernest Shackleton, the Shackleton's Adventure? Oh, children, how much you miss if you don't read. So you should read about Ernest Shackleton, because we've got his journal, we have his diary. It's so fascinating. And so it's not anybody's take on history, it's the real thing, because he was there. He brought back all the men. So it was the race to, they were down in Antarctica, and it was the race to the South Pole. So whoever could get there first, and their boat got, they passed Cape Horn at the bottom of South America, and they were getting into closer and closer with their ship, and they were frozen in place. So their ship froze. They were on the ship for 1 year, and then the ice was just crushing the ship. And when they realized it was like they had to get off. Then they lived on the glacier until some of the men got out in a little like dinghy type boat, made it, and somehow got them help. So it was a long time ago. No Coast Guard, no radios, all that. They ate their dogs. So I know my kids were like devastated as we were reading this. I said, "Oh man, I bet they're going to eat their dogs." And they did. They ate the sled dogs because they were so hungry. You go crazy, like eating ice and snow. You can't do that. So we went to. It was a rough ride, but good leadership. Fascinating story. I mean, fascinating story. Nobody died. One guy lost some toes, like to frostbite, and that was it. And there was a surgeon on board. He actually did the surgery and removed his dead toes. It's the most amazing story ever. And they had a great display at Mosey for years. It's gone, but where they had Shackleton there. Okay, so the last part of the chapter, he gets into something called the kinetic theory of matter. Notice it's the kinetic theory, not kinetic law. But as far as we know, atoms are always moving. So random atomic motion in 3 phases. Okay, so in the solid phase, they're just kind of vibrating back and forth. They can't move. So it's hard to believe that all the atoms in these tables are moving, but they are. They're just kind of vibrating in place. No place to go, really. If I took a blowtorch and liquefied the table, I'm providing a lot of energy to force that plastic to change phases, and now they're able to move around a little bit more. So they're moving around more. And if I continued the blowtorch thing, it's probably going to start stinking. It's going to off-gas. Some of those plastic molecules are going to escape, and some of them are probably being changed into other molecules. I'm breaking them down because I'm adding so much heat, and they're continuing to move forward. So in the gas phase, atoms or molecules move about faster than either in the liquid or solid phase. So this is why a substance changes from solid to liquid to gas as temperature is increased. And so the temperature at which a substance changes phases gives us 2 important little things to remember: melting point and boiling point. So if something's frozen, at what temperature point does it begin to melt? And if it is liquid, at what point will it begin to boil? So we know water boils at 100 degrees Celsius, 212 degrees Fahrenheit. And we know it freezes at 32 degrees Fahrenheit or 0 degrees Celsius. So your refrigerator, part of your refrigerator, probably hovers right around 32. So if you've ever shoved something to the very back, if you've ever gotten a kind of frozen a little bit. And some refrigerators are worse than that, worse than others, where you push something too far to the back and it kind of gets all icy and gets a little frozen. But it needs to keep it just really, really close to that to keep your food safe, so that you know that it's okay to eat it. And then your freezer's colder than 32. And so like the grocery stores, they actually have freezers that are just for ice cream, and they keep it really, really cold. Because, if ice cream kind of melts a little bit and then refreezes, it gets that granular, gritty taste. Have you ever had ice cream that like refroze? It's just something about it. It messes up the texture. And there's a whole science behind that, which is kind of interesting. But, so, when it refreezes, it makes little granules, and that tastes like grit. It's just not as creamy. You know how they solved that problem with cheap ice cream? They put antifreeze in it. So they do, and you eat it, which of course is terrible for you. And they don't have to label it. What do they call it? It'll be, my brain, the name of the chemical. Anyway, so they add that to that. So if you've ever got cheap ice cream with the long label, it's got antifreeze in it. So then no matter if it gets a little soft, when it refreezes, it keeps that creamy texture because of the antifreeze. So buy good ice cream. Just look at the label and just, you want like 3 or 4 ingredients. We made ice cream yesterday for young scientists in a bag. So it was half and half, a little tiny bit of sugar, and a splash of vanilla. That was it. And then we just squished it up. When we went home, I made it yesterday. We all ate it. It was delicious. So I added more vanilla.
Oh,
Yeah, so we just took a little small Ziploc bag, like a sandwich bag, and then you pour your cream in there, and then you put it in a quart or a gallon Ziploc bag with ice and salt, and then you just kind of keep smushing it. You kind of need hot pads because your hands get so cold. You kind of have little mittens or something. And it takes about 6 minutes, and then you have a whole bag of creamy vanilla ice cream. So now, if you were going to try to put strawberries or cookies in there, it probably wouldn't freeze very well. So you want to put that on afterward. And it's kind of soft, just like a soft serve. It's not like hard where you can just like scrape it, I left one of them sit in the sink for a while because we didn't eat it, and it got a little granular because it was just sitting with that ice. So part of it was trying to melt, and part of it was still cold. But anyway, just read your labels, and you can get good ice cream. Okay, so he says this is what we want to remember about the kinetic theory of matter. If you want to put it on a card, you can, but I bet in your brain this one's easy to remember. Molecules and atoms are in constant motion, and the higher the temperature, the greater their speed. Okay, so they're in constant motion, but the higher the temperature, the greater their speed. Okay. Now, we're going to talk a little bit about homonuclear diatomics, which is such a fun word to say. If you say homonuclear diatomic at the Thanksgiving table, all your relatives will think you're like a genius. So practice that word as Christmas is coming, and they might think, oh my gosh, my nephew's so smart, I better buy him a really great present because he knows all about some kind of, I don't know, diet or something. He's like a genius. He homeschools. They're so smart, those homeschool kids. Okay, so homonuclear diatomics, these are elements that don't like to be by themselves. And some of you might be a homonuclear diatomic. You don't like to go anywhere by yourself. Like I know sometimes we're at a restaurant and somebody has to go to the bathroom and go, hey, I gotta go to the bathroom. You wanna come with me? Okay, here, come on. Now sometimes it's just a good idea because you're trying to be safe, but sometimes you just like hate to be by yourself. You just want a friend. So we know that oxygen's like this. So, this is an oxygen atom, but you're not gonna find this in nature. They're always gonna be with another oxygen, always. Fluorine's like this. Nitrogen's like this. There's a whole list of them. That when you find them in nature, they're always going to be 2 of them linked together. So they're actually a molecule. Remember, 2 or more atoms linked together is a molecule. Now, that doesn't mean we couldn't just have one oxygen in a molecule, because he's got other friends, like H2O. So there's only one oxygen atom in a water molecule. There's only one, but he's got his hydrogen friends with him. That's okay with him. Does that make sense? Okay, so homonuclear diatomics, nitrogen, oxygen, chlorine, fluorine, bromine, iodine, astatine, and hydrogen. And you can put those on a card if you want to, too. He's telling you to memorize them. If you are, like I said before, chemistry is your jam. You're going to be a vet, a doctor, a dentist, then you probably should go ahead and memorize them. But if you're not, then put them on an index card. And some of them you're just going to always remember, like oxygen. You can just remember that. But just put them on a little card at the bottom of page 115. So you can remember who are homonuclear diatomics. And I'll tell you where it's going to come in handy. Sometimes we're going to write up chemical equations, and we're going to put 2 things together and write up our own reaction. Well, you'd have to know if you end up with just oxygen, you can't just put oxygen, you have to put O2. So it'll have to do with how we balance the equation, which we're going to start learning this week. So when we have a chemical reaction, so he's got one here like C plus O2. simple. We're gonna call these the products, and on the other side of the arrow, we're gonna call them the reactants. So products, work together to make reactants. Now, later on, we're gonna see something called an oscillating reaction, where then the reactants, it can run both ways. The reactants can work together to make go this way. But that's just kind of how we're gonna look at it. So carbon plus oxygen yields carbon dioxide. I can write that out with words he did in your book. Carbon plus oxygen yields, that might be the word we use for the arrow, yields carbon dioxide. So these are the chemical formulas for each of those things. And this whole thing together is called the chemical equation, and this process is called a chemical reaction. So from now on, this will never go away. So if you ever get like rusty on it, you'll have to come back to this chapter to remind yourself how to do it. Because we've already learned a little bit about stuff that we know that the law of mass conservation tells us that, matter's not created or destroyed. And the laws of thermodynamics tell us this too. So whatever's on this side has to be on this side in the exact same number. So it gets a little crazy because the numbers all have to match. So like if I had 2 molecules of carbon dioxide, we're going to do this just kind of like algebra. So we would say in this little bunch right here, that's 2 carbons, because here's my 2. I already have 2 oxygens, and so 2 times 2 is 4, so there's 4. So in 2 molecules of carbon dioxide, there's 2 carbon atoms and 4 oxygen atoms. Does that make sense? And that's what you're going to be doing. You're going to be looking at both sides and figuring out, okay, how many carbons do I have? Okay, carbons are same on both sides. How many oxygens do I have? Oh, shoot. There's not the same number of oxygens. And that's when you have to start. You can't change these little tiny numbers. You can never change the subscript. You'd be changing the substance. You can't do that. But you can change how much you add. It's kind of like a recipe. You can see it's kind of like a recipe. So you can if you're doing a recipe and you're doubling every single thing, you're saying, then it should be the exact same recipe in the end, right? Only like something really weird, like you're making fudge or caramel. Sometimes if you've got a huge pot and you're boiling something, a doubled recipe makes that temperature hard to attain. But in general, if you're making chocolate chip cookies, whether you're making 1 batch or times 5, if your mixer can hold it, it's the exact same thing. You're not changing anything, you're just making more of it. So we can add more molecules, we just can't change any of those little tiny numbers trying to match everything up. The sad thing is sometimes if you change 1, now you've messed everything. Now you messed up something you already had balanced. It reminds me of those puzzles. Remember the puzzles that they're flat and they got the little squares that you slide around? Have you ever played with one of those? They're like something you get like in a treasure box at Sunday school or something. There's like a little square, flat square, and then you slide little squares. You know what I'm talking about? They were like a big thing when I was little, but I'm old. So you're moving around, you're going, okay, this is great. I got all the books of the Bible in order. And then there's like Habakkuk. It's just sitting there. You're going, shoot. Now to get Habakkuk back to where it goes, oh man, that whole thing's messed up now. So then you just pick it apart, like the Rubik's Cube. My brother took off all the stickers and just put them like right. We thought he was a genius. He was like 5 and he solved the Rubik's Cube. My brother can solve the Rubik's Cube. But then he confessed he picked up all the stickers and just put them back on. So you feel like doing that with a chemical equation, but you're going to figure out how to do it. And he's even going to give you some methods next module where we can use like some fraction method to like almost like where you're looking for the same common denominator. It's a fabulous method. I'll tell you this, I never learned it. And all through high school and all through college, they never taught the method he teaches in this book. Would have saved me hours. Because when you're solving a really difficult equation and you're trying to balance it, it's all guessing. You're just guessing. So it's kind of tedious, It's not really hard. It's just okay, try it again. Let's try 2 molecules of that. Yeah, messes up these and messes up that. All right, let's try well, then we can have 4 molecules. It's just kind of like a give and take. It's messy and it's slow. So he gives some methods that will speed that up, which is really cool. I can't wait for you to learn that. So what we're looking for is a balanced chemical equation where we have the same number of atoms on one side as the other. Not necessarily the same number of molecules, same number as atoms. So we're looking at the individual little letters. Okay. All right. Well, we're not going to do this because we're going to do what is our lab? What are we supposed to do? How about some? Oh, that we really don't have anything to do.
You're gonna do hot glasses.
Yeah, that's really dumb. I guess we could do that. I got 2 jars. If you want to give me hot water and cold water, I got some ice in there. Shoot, I just looked at my notes. Maybe we'll do it another day. Like this summer, I was looking through labs and trying to see where it was a really boring day and then putting something fun. And if it weren't for the hurricane, we would have done it. But I bought some sodium alginate and some calcium chloride, and you can make water spheres. Have you ever seen the little edible water balls? Have you ever seen that online? Like, you can see it on Pinterest. People do it with juice. Has anybody ever made them? People make them with like juice, and so like think of Orbeez. So they feel like an Orbeez, but when you like bite it, it's like there's water in there, and it just like disappears in your mouth. So it's really cool. And so some people make them with like fruit juice. So you've got like grape juice or apple juice, and then literally people like scoop them up like with a serving spoon, and then it looks like caviar, giant caviar balls or Orbeez or something. But when you eat it, it's like they bust in your mouth and it's juice. I thought that's so cool. We got to do that. Which maybe we will. So I got the chemicals to do it. It's all edible. So I just bought food grade sodium alginate. Now this is like a foodie thing, that they do, these little edible balls. And then people, I think, do them with alcohol and stuff too. So if you look online on Pinterest, you'll see lots of recipes for it. It's not hard to find the ingredients, but sodium alginate, calcium chloride, what you need. So it forms a little skin. And so you drip with a pipette. You drip them depending on how big you want your little spheres, whether you drop it with a spoon or a pipette, and they fall like in oil or something, and then they create a spherical shape. It's really cool. It's really cool. And you drop it in. Did you make this?
No.
Okay.
I've seen it.
You've seen it. Okay. Well, I actually did it. I've actually done it with little kids, but we didn't do water or juice. We just it was almost like making an Orbeez, and so the other way you could do it is we would squirt it out real fast, and it makes like worms, and then you can pull them out. So like if you do no coloring, if I put no coloring in it and I squirt it in there, it doesn't look like anything, but you stick your hand in there and then you pull it up, there's just clear streams. It's really cool. So fun, totally non-toxic. Okay, one of these is cold, one of these is hot. I just need, you don't have to write this up because it's really dumb.
You want to spread it?
Yeah, that's fine. Oops, except for I gotta let this sit for a while. They're both jiggly. So jiggling would be an experimental error, because what we want to see is if I put red food coloring in the icy cold jar, it's going to take longer to disperse than in the hot jar. But sometimes, let's see, I already bumped it again. They're both jiggling. If it jiggles, it just really, it's kind of down. So this is still jiggling, I guess because I'm walking on here. Yeah, he's still jiggling. They won't stop jiggling. They're not participating. So if they were very still, it would help. You're giving me red. So when you stop me, you jiggled it. See? Now you jiggled it more. Okay? You wrecked the whole lab! I don't think it's going to work because of too much jiggling. We'll see. See if he's still jiggling. I don't know if you can see the hot water is really jiggling. Which is not really fair. But I'll try to put them both on the side. See, I don't see some kind of huge difference, do you? Now, I do kind of see sometimes in the cold one, it seems to sink a little bit. I don't know, you guys can watch and see if you think it makes a big of a difference. To me, I don't ever see a huge difference. And I think it's because already the water molecules are kind of all busy because they've been jiggled. Jiggling is always a big experimental error. Kind of a density thing too. To me, the cold one looks like it's dispersed better almost, but maybe because the ice has taken up so much space. Yeah. This isn't oil-based, this is water-based, but I think the cold one, I think they're the same. So, don't write that down. But in reality, if we could get these perfectly still, then the cold one would take longer to disperse than the hot one because there's not as much energy in the system. So the hot water is giving energy to those food coloring molecules and making them spread out faster. Don't not practice there's some examples in your book and then you'll have the on your own. And it's tedious, but in the beginning, do that where he writes out every single thing where he says, okay, how many H's do I have? How many C's do I have? That will really help you. So you won't always have to quite do it like that, or you're always going to probably have to scrabble down something. Because you just want to make sure you're looking to see if everything's balanced. So then once if you change one of these numbers, the number of molecules, then you got to go back. You may have had something balanced before, but you better go back and check now because you may have messed it up. Because it may be in a molecule over here, and now it's the other one's off. So you got to keep practicing on that. This is the last of the really easy stuff. Not to scare you or anything, but this balancing chemical equations gets a lot harder because they're longer and there's more molecules involved, and so it's a little bit trickier. So those of you who weren't here, hey, those of you who were here last week, did you already write up your lab? You did? Some people did. How many people did already write up their saltwater lab? Okay. All right, so at the top of your lab, when you turn it in, write extra credit real big. Okay, so good for you, extra credit. I'll give you extra credit. But if you didn't write it up, now you don't have to. Now, if you came last week and you want to write it up, then I guess you can extra credit too. Yeah, okay, so, but it's just a waste of time for you guys to write that up that you didn't do. Please do read it. Read the little green box. Do read it. But I don't want anybody getting behind. We just need to get right back to life as we know it, whatever that is. And so just when we start 5, then we'll be nice and crisp, and hopefully everybody can be here. And so we're going to go over test number 4 right now. So that would mean there'd be no labs required in your next folder, unless you're going to be an overachiever and an early rider like Jordan, and you can get extra credit for that. All right, so let's look at your test. Test number 4. Where are you, test number 4? Here it is. Test number 4. So next module, it's going to be almost completely about balancing chemical equations, literally where we're counting molecules and atoms in the equation. And we're going to learn about 3 basic types of chemical reactions: decomposition, formation, and combustion reactions. So a combustion reaction is always the same. You always yield carbon dioxide and water, which is why you actually, when you digest your food, you're actually undergoing combustion. Now, you don't blow up, but it's the same chemical equation, which is so interesting, and which is why, if you remember from biology, it was kind of tricky in the cell chapter. We talk about cellular digestion, and you remember words like the electron transport system and the Krebs cycle. It's a little weighty, yeah. My dad used to always scare me. He'd go, "Oh my gosh, the Krebs cycle! I had to have a whole class on just the Krebs cycle." And I was going, "Please stop," because like my roommate was telling me how terrible the unknown. I told you how I got aluminum, and so God helped me through. He even helped me through the Krebs cycle. But it's really a miracle, because your body has to allow that energy to escape gently, or else you would blow up. So it's like poof, 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 like that instead of poof, like that. So if you just combusted your food like you roast a marshmallow over a fire, you would have a problem. So that's something that even shows up in biology. So we're going to talk about that next week. Okay, test number 4. First question: what are the 4 classifications that we learned for matter? What are the 4 classifications we learned for matter? This is test number 4. Wrong test. Oh, wait a minute. That's not right. Okay, so we could say an element, a compound, a heterogeneous mixture, and a homogeneous mixture. I'll say those again. What are the 4 classifications of matter that we learned about? We learned about elements. That's everything in the little boxes on the periodic table. Compounds, heterogeneous mixtures, and homogeneous mixtures. That was somebody bringing donations. Did you get that email, Ashley, about donations?
No.
Pat Perkins' son is taking stuff down south, and he just said, bring anything you want: water, generators, food. And I got it late last night, so I would have been great. Everybody could have brought something. It would have been fabulous, but maybe he'll do it again. It's such a great idea. I saw somebody online doing that. They just fill their trunk with junk and drive down there and open their trunk and go, "Hey, do y'all need anything?" And people just grab it. You can only hope that people that really need it grab it, but why would you be down there if you didn't
Well, they
need
are
stuff?
down there because
What?
I said they are down there because they're looting the house
That's so horrifying.
It's so horrible, yeah.
Okay. All right, 4 classifications: element, compound, heterogeneous, and homogeneous mixtures. Okay, that was number 1. Number 2, what are the 2 classifications for the changes that matter undergoes? We just talked about it. We said we could chop up the wood or we could burn the wood. What are those 2 things called? A what change and a what change? A physical and a chemical change. Yep. Yep. My physical science students might get past this test, so don't blow this one. It's an easy one. Okay, that was number 2, physical and chemical. Physical and chemical. Number 3, if a substance is an element, is it a pure substance or a mixture? If I find it in the periodic table, it's in a little box. Is it a pure substance or a mixture if it's called an element? What do you think? Pure. It's a pure substance. That's right. I got a little pile of sulfur. My little strip of aluminum in my unknown. They gave everybody a pure substance when I did that lab. They would never have given someone a compound. You just trying to figure that out would be a whole nother level of chemistry. This was first year chemistry. So everybody got a pure substance. Might happen. Such a happy day. Okay, number 3. If a substance is an element, is it a pure substance? I just asked you that. Number 4. Classify the following as element and compound, homogeneous mixture or heterogeneous mixture. Okay, so a fruit salad. What's a fruit salad? Is every bite the exact same? No. So it's all mixed up, so it's a heterogeneous mixture. So A is heterogeneous. Fruit salad is heterogeneous. Heterogeneous mixture. Okay. B, aluminum foil. What is aluminum foil made out of? Aluminum. Is there anything else in it besides aluminum? No. Okay, so it's what? It's in the little box, so it's an element. It's an element. So B is element. B is an element. Aluminum foil is really just an element. Anybody's mom still call it tin foil? Or your grandma call it tin foil? Ever heard anybody say tin foil? Because it used to be made out of tin. You still call it tin foil? It's been made out of aluminum for a really long time, but it used to be made out of tin, so it would actually rust, like it would get grody. You know, like if you found some old trash or something, it would be kind of rusty. Okay, C is a pile of CaCO3, calcium carbonate, CaCO3. Yes, it's a compound. Yay! Timothy, did you say that? That was good. Timothy also rightly predicted that Tampa would not be hit by the hurricane. And I told everybody about you. I said, yeah, one of my students says it won't hit Tampa. First he told me it was a rumor, but the better word is legend. It's a legend.
I did hear, and I don't know if it's to do with that, but they said that it would be impossible for it to hit Tampa Bay like it hit the others. And I don't know if it's...
Well, it's a harbor, first of all,
No,
but
because they said the way that it pulls out, it can't...
it's the timing, though.
Yeah.
If
No,
it had hit us at high
I
tide,
did
it would have
something.
flooded the city, for sure. But anyway.
Well, I don't know where I heard it.
And then the meteorologists were standing there,
Not
because, it did the same thing it did with Irma. It sucked out Tampa Bay, and they're going, this is so bad. I'm going, no, it's not. That's so good. Are you crazy? They said, this is not what we would expect at all. This is bad. I'm going, maybe bad for your news, but it's great for the city of downtown Tampa. It's not going to get flooded now. They get water during a regular storm. Okay, that was the CaCO3 was a compound. And the last one is fertilizer dissolved in water. That's hard. That would be like salt dissolved in water. So we're going to call that a homogeneous mixture. It is a mixture, but it's homogeneous. Once it dissolves in there, every little section I tested is going to be the same. So homogeneous mixture. Okay, let's go over them again. So A was fruit salad. That was a heterogeneous mixture. B was aluminum foil. That was an element. C was the pile of CaCO3. We said that was a compound. And D was homogeneous mixture, and that was fertilizer dissolved in water. Number 5. What are the differences between solid HCl and liquid HCl? Well, he says solid HCl occupies less space. The molecules are closer together, and they move slower. Okay, so we're going to say takes up less space, molecules closer together, and moves slower. Occupies less space, molecules closer together, and they move slower. So 3 things are true of the difference between solid and liquid HCl. Could we say that about water? No, we could not. Okay. We would say, they have to say that solid water takes up more space. Okay, so it takes up less space, molecules closer together, and they move slower. Everybody got that? Number 6. If a substance goes from the gas phase to the liquid phase, was it heated or cooled? It went from a gas to a liquid. To do that, do we heat it or cool it? We had to cool it, yeah, we had to cool it. We had to take away energy from the gas, from the molecules. They're very energetic. We got to calm them down, and as they calm down, that's going to bring them closer together. Okay, so we cooled it. And that's what we call condensing. So think about like dew in the morning is condensation. So it's coming, the water is in the atmosphere, and in Florida, plenty of that. And then when that comes in contact with that cool grass or the cool metal car, then it condenses, and then you get liquid. Okay, number 7. Ice floats in water. Does frozen HNO3 float in liquid HNO3? No. So that's what's so weird about water is that the ice floats. I don't think it's in this book, or I think it's in physical science. He wanted you to take a stick of butter, melt the butter, and then take another stick of butter and just drop it in the liquid butter. And you'll know the chunk of butter just falls to the bottom. It doesn't float. And so that's true of almost every other substance. And I guess he had you use butter because it's like for homeschooling, and most people would have maybe a stick of butter in their fridge. But other substances aren't like water. They're not participating in hydrogen bonding, so the ice is actually more dense, so it sinks to the bottom. So the answer he wants for this one is no, it does not. Frozen HNO3 does not float in liquid HNO3, so we're going to say no, and that's number 7. So say no. Number 8. Classify the following changes as physical or chemical. Okay, ABC. A lawn gets mowed. Is that physical or chemical? What do you think? Physical, yeah. You just chopped it down. Okay, a frozen turkey thaws. Is that physical or chemical? That's physical. Physical. There's no change. What about a wood burning in a fireplace? That would be chemical, right? So now, if instead of the lawn getting mowed, you poured acid on it, that would be a chemical change. If instead of a frozen turkey being thawed, you threw it in a fire, and it burnt it, that would be a chemical. So see, wood. Okay, number 9. Which of the following elements are homonuclear diatomics? Write their chemical formulas. Okay, you're not cheating if you pull out your index card, and because I already told you you're allowed to use that. So if you're not going on in your chemistry life, then this will be sort of a freebie, okay? Because he's going to give you a list of atoms, and you're going to pull out the ones that are listed as homonuclear diatomics. Okay, so he lists carbon, nitrogen, fluorine, and sodium. And of those 3, you've got nitrogen and fluorine. Nitrogen and fluorine are homonuclear diatomics. And then he wants to write the chemical formula. So you would write N2 and FL2. Excuse me, not FL, that's fluorine. Into, what is fluorine? FL2. What's FL? On my chart. I'll look later. Okay. N2 and F2.
FL2 or F2?
Just F2. F. I told you FL, but it's not FL, it's F. Fluorine is F. Okay, that's number 9. N2 and F2. Number 10. Is the following equation balanced? The answer is yes. Just because I'm going to write the other ones out for you, but that one I'm not going to write. So because he's got H2O plus Na yields NaOH plus H2. And if you count all the H's, they're the same. If you count all the O's, it's the same. If you count all the Na's, it's the same. So the answer is, this is number 10. Number 10 is yes. Number 10 is yes. Okay, number 11, he wants us to balance the following equation. I'll put that one on the board for you. H2O plus Na. Notice he gave us some phases in there, which don't really matter. He just did NaOH. Oh, this one we didn't mention. AQ means aqueous. That means dissolved in water. plus H2 gas. Okay, so this is not balanced. How do I know that's not balanced? Well, I have too many hydrogens on this side. So I've got 2 hydrogens on this side, and I've got 1, 2, 3 hydrogens on that side. So we know for sure hydrogen doesn't match. What about oxygens? I've got 1 oxygen here and 1 here, so that's okay. Sodium, I got 1 here, 1 here. So really it's just my hydrogens that are messed up, right? Okay, so how can I fix this? He's got you adding 2 water molecules here. And that. Okay, that should be balanced. Let's see if it is. Okay. So I've got 4 hydrogens here, 2 hydrogens here, and 2 hydrogens here. That's 4. So hydrogen's balanced. I've got 2 oxygens here, 2 oxygens here. I got 2 sodiums, 2 sodiums. Everything's balanced. Okay, so what he did probably first was trying to find out, and that's where that common denominator comes in, because we had if we could make 4 hydrogens, then we could make them into a 4 by doing 2. So if I added 2 water molecules, I fixed hydrogen, but I messed up sodium. So okay. Now everybody's happy. So when I fixed my hydrogens, that's what gave me my 2 sodiums. I had to come back here and give myself. Basically, what I'm figuring out the recipe. We want this to run with no leftovers. You see what I'm saying? So it'd be like, we never do this, but like if you were going to make chocolate chip cookies and you only wanted a certain amount of flour, maybe you were going to an old-fashioned store that they would literally weigh out your flour. There was a little place in Flint City, they didn't keep doing it, where literally they just had big, like, things of flour, sugar, spices, and then you told them how much you wanted, and they had a little scale, and they would weigh it out for you. So you could, she was saying, and then you don't have to waste anything. So you got a recipe, and you need all these spices, then you don't have to buy a bottle of everything and have them all left over. And it was a great idea, it just didn't catch on. And so then she would weigh all those little spices, you'd have a little bag, and you paid like $1 versus $20 buying 5 different spice bottles. So it was clever. There's no money in it. So that way you didn't have any leftovers. We want this to run so there's no leftovers. Okay, that was number 11. Okay, number 12. Under the right conditions, chlorine gas will react with gaseous ethylene, C2H2, to make liquid quadrichloroethane. Write the balanced chemical equation. Okay, so now he's giving you words, so you have to put the words into the little molecules and write your products and reactants. Then you have to balance it. So he's just giving you one more step. Okay, so in the end, what number was that one I just wrote up there? Number 11. I'll write an 11 by that. Probably after this module, what I start doing is writing all the math on the board for you, like ahead of time, and that way y'all can just take a picture of it. Does that make sense? So I'll do that, like probably starting next module or the module after that, because it gets really, it's too much to write down while especially if we have a lab. Like today we didn't, so we had more time. Erase these right here. Number 12. Okay, I'm going to go over that with you so you can kind of see what I did. That's the answer for number 12. But the question said, under the right conditions, chlorine gas, so that's when I wrote my Cl2, it's a homonuclear diatomic. So I had to know 2 things. I had to look up chlorine on the chart, see that it was Cl. I had to know that it was a homonuclear diatomic. It was on my card, so I had to put a little 2 right there. I put a G because it told me it was a gas. So I knew 3 things about that from just what I read when he said under the right conditions, chlorine gas. So I got my Cl, it's homonuclear, I put my phase. Okay? Under the right conditions, chlorine gas will react with gaseous ethylene. He gave you that chemical formula, C2H2. He gave it to you, but he said it was gaseous, so I put the little G. Okay? And then he said it will make liquid quadrichloroethane, and he gave you that. He gave you that too, C2H2CO4, but he told you it was liquid, so you had to write the little L. Does that make sense? So this was a given, and that was a given, but the phase he used in words, you had to put it in parentheses. Now you have to balance it. So first you had to write it, then you had to balance it, and this is the way it is balanced. All are the same. Okay, that was number 12. Number 13, I'm gonna write that one up here for you. C9H20. That's 14. That's a whopper. Okay, so that's the balanced answer. This is number 13. He says, when C9H20, okay, reacts with oxygen, so I had to write O2 because it's a homonuclear diatomic. It makes carbon dioxide and water, CO2, water. He didn't tell you that. He expected you to know that carbon dioxide was CO2 and that water was H2O, but you know that. Okay, then I had to balance it. Look at that, how high you ended up with. That was tricky. So I wish he'd gone ahead and told you the fraction formula. We're going to do that next module. But by trial and error, you're going to get all the way up to 14 oxygens. Okay, so let's count. We've got 14 times 2, that's 28. And then look, you still have one here in the H2O. And then we have to count on the other side. Oh, it's kind of small. 9 carbons. I've got 9 carbons here. That's probably where you should start, because you got 9 carbons here, and you make the 9 carbons here, and that's how you ended up with all the oxygens. And see, right here is 9 times 2 is 18 oxygens right there. You see what I mean? And you have another one here. 19. Okay. It's 14. Make sure I told you right. I did. Okay. You can read my scrawl. Okay, the last big equation is 14. Let's see, 2H6 plus O2 gas yielding 2 carbon dioxides and gas. That's 3 water molecules. And gas. Okay. Got phases there. Here's what he told us about 14. He said, balance the following equation for the combustion of ethanol. Okay, so he actually gave you the equation, so you didn't really have to do anything but balance it. So you would copy down the one that he did, and then you start balancing, and you can see you end up with 3 oxygens on this side. And let's see, that's, yeah, 2 carbon dioxide molecules and 3 water molecules. Okay, that one's actually a little easier, but you got 2 things to balance. Okay, number 15, and it's the last one. We'll get done a little bit earlier now, a little bit. Okay. Number 15 said, how does a balanced chemical equation ensure that mass is being conserved during a chemical reaction? His answer is, if a chemical equation is balanced, then the same number of atoms appear on both sides. This would mean that the mass is the same whether we're talking about reactants or products. So when we balance a chemical reaction, that's what we're doing. So we're making sure that they're the same. Nothing disappeared in our when we reacted these 2 things. Now in real life that's not going to happen, but when you write it out on paper, you got to show that didn't happen. That there was no leftovers, and there wasn't anybody that didn't have enough. Okay, so a balance. How can we put that in smaller words? Let's just say, if the atoms are the same on both sides, the mass is the same on both sides. Let's say it like that. If the atoms are the same on both sides, the mass is the same on both sides. Does that make sense? If the atoms are the same on both sides, the mass is the same on both sides. Anybody got a question? Of one we looked at? Yes. Which one? Right here? Oh, AQ. Sorry, it looks like a Q. Q, aqueous. So that means something dissolved in water. This is probably in your reading somewhere. So we've got L for liquid, G for gas, S for solid, AQ is aqueous. So it's something that's dissolved in water. So it's not really liquid, it's like dissolved in water. Anybody else got a question? Very good. Okay, so, hey, if you didn't turn in a folder for your stuff last week, I'm probably sorry, so we'll just put it in with your folder next week, so that's all together. There for grading, we